Welcome to this explainer. Let's jump right into a pretty massive irony of the green energy transition. As we're racing to build this carbon neutral future, the very climate change we're trying to fight is actually breaking the AI tools we designed to manage our clean energy. Crazy, right? Because building all these massive wind and solar farms, that's really only half the battle. Actually predicting how much power they're going to generate, that is what keeps the lights on, and the stakes couldn't be higher. When these forecasting tools fail, it's not just some tiny data error on the spreadsheet. It means utility companies are suddenly scrambling to buy emergency power, which makes your energy bills absolutely soar. In a worst-case scenario, we're talking rolling blackouts during extreme heat waves that threatens critical infrastructure, and it literally threatens everyday lives. So why exactly do the tools meant to manage green energy fail right when the weather gets extreme? To answer that, we're going to investigate a fascinating failure that spans two totally different ends of the spectrum. First, the immediate minute-by-minute forecasting of power grids during sudden, violent storms. And second, the long-term, multi-year forecasting of equipment life cycles. By that, I mean the physical hardware, the massive steel turbines and thousands of acres of solar panels that are physically aging out and needing replacement. Predicting the grid means predicting both the next 5 minutes of weather and the next 15 years of hardware. And right now, both are critically failing, and for surprisingly similar reasons. Let's look at some actual data from the massive R2 Energy benchmark. This is a study that analyzed over 10.7 million records across China, and it shows us exactly how extreme weather completely rewrites the rules of energy generation. The contrast is just staggering. Take a severe rainstorm. Solar capacity absolutely plummets by more than 50%. Why? Well, thick, heavy cloud cover physically blocks the sun. Pretty straightforward. But for wind power, a rainstorm does something completely different. It totally scatters the data. Sure, it shifts the median power generation upward, because of the storm's raw energy, but it introduces this massive, unpredictable, chaotic turbulence compared to the steady breezes you'd get on a normal day. It is an entirely different, incredibly complex environment for an AI to try and predict. Okay, let's really dive into the core issue here. The primary problem in grid management today is that our forecasting AI models are largely judged on their average accuracy, a metric data scientists call mean absolute error. But relying on this creates a highly dangerous average illusion. Think of an AI model kind of like a driver on the highway. A model that performs well on average is like a driver who is perfectly safe on an empty, straight road on a sunny day. But they completely panic and crash the second there's heavy traffic and rain. Judging a model on how well it performs on a mild, breezy spring day completely obscures how fragile it is when severe weather strikes. And grid operators, they need reliability in the chaotic traffic of a storm, not just on the empty highway of a clear day. This brings us to a really crucial concept, the robustness gap. Think of it as this hidden, critical vulnerability just ticking away in the background. See, an AI forecasting model might look highly reliable on a sunny Tuesday. It boasts these incredibly low error rates that make utility executives very happy. But under extreme meteorological conditions, these high-impact, tail-risk weather events like a sudden torrential rainstorm or a prolonged heat wave, that exact same model can fail catastrophically. Just imagine being a grid operator in a control room. You're trying to balance the power load for millions of homes, a sudden storm knocks out gigawatts of expected power, and your forecasting AI is still confidently telling you that everything is perfectly fine based on its average programming. That, right there, is the absolute danger of the robustness gap. So where does this vulnerability come from? The root of it actually lies in the fundamental physical differences between our two main renewable sources. To truly understand why these complex AI models fail, we've got to contrast the physical reality of how they generate power in the first place. Solar power is what we call pattern dominant. It follows deterministic, highly predictable diurnal cycles. The sun predictably rises and the sun sets. Wind power, on the other hand, is noise dominant. It's heavily influenced by turbulent, localized gusts and what meteorologists call synoptic transitions. Those are broad, large-scale shifts in weather systems, like massive cold fronts sweeping across a continent. We're talking about two completely different physical modalities here, and they demand entirely different mathematical modeling capabilities. When these distinct physical modalities react to the exact same storm, the results are drastically different. Like we talked about, rainstorms drastically suppress solar output due to thick clouds. Now, in physics and data science, a storm is a high-entropy event, meaning it's highly chaotic and unpredictable compared to a normal day. But for solar, it still results in a fairly predictable suppression of energy. Wind generation, though, Rainstorms, which are typically driven by convective systems, introduce massive chaotic turbulence. The wind fields become highly volatile and just jump all over the place. So a single AI model operating on the grid has to somehow handle both the predictable drop in solar energy and the completely unpredictable chaos in wind energy, all at the exact same time. So how does modern AI handle all this extreme turbulence? Well, the benchmark data reveals a massive plot twist. You'd naturally assume the biggest, most advanced, most heavily funded AI architectures would perform best, right? Actually, no. During high-entropy, chaotic events like storms, sophisticated, state-of-the-art transformer AI models fail catastrophically. The data shows they completely collapse. They perform even worse than primitive physics-based baseline models. Meanwhile, simpler, autoregressive, or AR models stay surprisingly robust. AR models, specifically ones utilizing gated recurrent units, basically just look at sequential data step by step, rather than trying to digest the whole universe of data all at once. And these simpler models maintain their accuracy remarkably well, even when the weather goes completely haywire. It is a stunning example of how bigger definitely isn't always better. The crucial question is, why does this happen? Why do the fancy high-tech models totally faceplant? It all comes down to exactly how they process information. Massive transformer models use something called global attention. Basically, they try to look at the entire timeline of data all at once to find big picture semantic patterns. But by doing that, they get completely distracted by the macro view. They end up washing out the immediate high-frequency turbulence of a sudden storm, treating it as if it were just background noise. Simpler autoregressive models, however, predict things step by step. They dynamically inject weather data exactly as it happens. This beautifully mirrors the immediate physical causality of a sudden gust of wind violently hitting a turbine blade. This leads to a massive, really frustrating irony and efficiency. Those complex transformer models, they cost vastly more computational time and energy to train. We're talking huge server farms sucking up massive amounts of electricity. Ironically, the very electricity they're trying to manage just to run their algorithms. They're expensive, they're heavy, and they're slow. Yet they perform drastically worse in extreme weather than simpler, lightweight models like multi-layer perceptrons, which are basically just streamlined neural networks. The models that dynamically inject weather data step by step aren't just more accurate when the grid is literally on the line, they require a tiny fraction of the computing power. Sometimes, actually, scratch that, a lot of the time, a simpler, more grounded approach just works better. But immediate power generation isn't our only forecasting failure. We really have to zoom out and look at the whole picture here. Our inability to forecast the digital generation of the grid, the actual electrons flowing through the wires, is perfectly mirrored by our massive blind spot in forecasting the physical hardware of the grid itself. As millions of solar panels and wind turbines are installed globally, our ability to forecast when they'll come offline, when they'll break down, and where their raw materials will ultimately go is virtually non-existent. According to research by the Ellen MacArthur Foundation, predicting the scale of wind and solar decommissioning is nearly impossible right now. Why? Because we completely lack reliable tracking platforms. We simply don't have spatial or temporal data on these massive assets. On top of that, inefficient tech is being retired early, supply chain coordination is incredibly poor, and private companies just aren't disclosing their life cycle data. And the scale of this problem is deeply alarming. We are talking about millions of tons of heavy solar panels and gigantic fiberglass wind turbine blades silently aging, destined to pile up in landfills because we don't have the closed-loop tracking data needed to manage their end-of-life cycle. We are forecasting completely in the dark here. Whether it's a fractured, disjointed supply chain completely failing to track retired solar panels, or a highly expensive, energy-hungry transformer AI totally ignoring the physical reality of a turbulent windstorm, the common denominator is striking. In both cases, we are seeing a dangerous, growing detachment from physical reality. We're building massive data systems and AI models that look incredibly impressive on a spreadsheet or in a highly controlled, average-case testing scenario, but they completely lack the real-world, step-by-step grounding needed to actually function under stress. We are confusing digital models with the physical reality of broken turbines, sudden storms, and overflowing supply chains. The researchers behind the R2 Energy studies summarize this perfectly. They say, reliability is driven by the alignment between a model's inductive bias and physical causality rather than mere architectural complexity. In other words, it doesn't matter how complicated, massive, or mathematically brilliant your AI architecture is, if its underlying logic doesn't precisely match the actual laws of physics in the real world, it is going to fail. In safety-critical systems like our power grid, throwing bigger, more complex technology at a problem just isn't always the answer. If an AI loses touch with the physical cause-and-effect reality of a storm hitting a turbine, it stops being an asset and immediately becomes a massive liability. Which leaves us with this final provocative thought to consider. We know without a doubt that the climate is changing, and extreme weather is rapidly becoming our new normal. So, as our environment grows increasingly volatile and chaotic, how can we build AI and data systems that truly understand the physical limits of our planet? Ultimately, the clean energy transition is every bit as much a data challenge as it is a physical engineering one. If our clean energy future relies on these digital systems, we have to make absolutely sure they are firmly anchored in reality, not just average case illusions. Thanks for joining me on this explainer, and keep questioning the data.